Hai, salam sejahtera. We are from Group 1 and today we're gonna present about our mathematics engineering group project with the title Local Extreme Value. And this is our group member. The first one we have No Ashikin, second one is Xie Xiang Feng, and the third one is Oizi Kwan. The number four is Go Jun Hong, and last one is me, Tan Mu Xian.
Hi, for the introduction, I will actually explain to all of you guys about it, which is in engineering, we need to understand about the design or the system work in order to know whether the design work well or even has the safety of the factor. So one important idea, which is we call it as local extreme value, since we know the point which is it is either the highest or the lowest point. That totally rely on the strongest stress in a beam of the lowest cost in a process. So to find this point, we need to use the calculus or even engineering math, which is the first derivative tell us where the slope is flat, then the second derivative help us to see whether there is a peak or even the minimum, which is a peak and a dip. So even though this sound easy, it can be hard to use in real life because for the problem statement, a civil engineering is analyze the temperature distribution on a concrete slab exposed to sunlight. The temperature at any point on the slab is modeled by the functions txy 70 plus 5x minus 4y minus x squared minus y squared plus 3xy, which is txy is the temperature in darajah Celsius at the point with coordinate xy, and x and y are the horizontal distance in meter from the fixed corner of the slab. For the A, which is we need to find all the critical point of the temperature distribution on the concrete slab. Meanwhile, for the B, we need to use the second derivative test in order to determine whether each critical point is a local maximum, local minimum, or the saddle point. And for the third one, which is we need to estimate the temperature at each critical point and explain what this tell the engineer about possible hot spot or cool spot on the slab. This finding will help guide decision for insulation or cooling system to prevent cracking or thermal expansion. So for the objective, there are three objectives for this group project. The first one is to determine the critical point of the temperature function as it can locate area of potential hot or cool spot on the slab surface. The second one is to employ the second derivative test to determine whether each critical point is local maximum, local minimum, or the saddle point, indicating temperature behavior in this location. So the third one is to support engineering decision about the placement of the insulations, cooling system, or the expansion joint based on accurate thermal analysis.
Good morning, lecturer. I'm Go Jun Hong. So now I'm going to talk about fila table. So for our fila table, we have three parts. So for the first part, the facts is the temperature function is given as the below equation. So the ideas that we use is by using partial derivatives to find where the temperature changes most rapidly. So by using this, we can find and classify critical points of a multivariable functions. And the action plan that we use is to find the fx and fy. Then we solve it for the point where both are equal to 0. So for the second one, critical points are where the first derivative is equal to 0. By applying the second derivative test to determine whether the critical point is a local maximum, local minimum, or saddle point. For the learning issues, is how is the second derivative test used for multivariable functions? What is the determining test used? So the action plan that we take is to compute txx, txy, and tyy. Then we use the Hison determinant to calculate it. And the last one is engineering applications needed to know if hot or cool spot exist. By translate mathematical results into physical interpretation. For the learning issue is how to relate set points to real engineering decision. And the action plan that we take is to explain the saddle in the context of heat flow and suggest insulation or cooling recommendations. Okay, so for the next one is methodology. So we have three methodology to calculate these projects. So for the first one is mathematical model temperature distribution. It is to analyze the temperature distribution on the surface of a concrete slab by using the below equation. And the second one is first partial derivatives. Is to find the critical points of the temperature distribution on the concrete slab. And the last one is second partial derivatives and Hisse matrix is to classify the critical points by using Hisse determinant method, which is G equals to fxx, fxy minus bracket fxy squared.
So answer the doctor. My name is Xiang Feng and I represent the solution part. So the first question, find all critical points of the temperature distribution on the concrete slab. So the equation will shows in the first, and then we just differentiate the x part and y part into the fx and fy. So we take the x part into the first equation and the y as a second. So we use the first equation to substitute equals to y. So we know that y equals to 2x minus 5 per 3 as a third equation. So we put the third equation into the second equation. So we know that x equals to 2 per 5. And after that, we can find the y equals to negative 7 per 5. So the critical points of the temperature distribution on the concrete slab are 2 per 5, comma, negative 7 per 5. The second question. Use the second derivative test to determine whether its critical point is a local maximum, local minimum, or saddle point. So to find the critical point is what type of things. We need to more differentiate more against, which is SS, YY, and SY. So we know that SS equals to negative 2, TYY equals to negative 2, and SY equals to 3. So we use the formula G equals to FSS times FYY minus FSY with the square to evaluate the GAB. So to evaluate the G, we assume that it's 0.0. So we know that after G 0.0 is negative 5, which is smaller than 0. So we use the case tree, which is know that FSY has a saddle point FAB. Therefore, T 2 per 5, comma 7, negative 7 per 5 has a saddle point at 0.0. Besides, because of GAB is smaller than 0, there's no local maximum value and no local minimum value. That's it.
For the last question, estimate the temperature at each critical point and explain what this tells the engineer about possible hot spot and cold spot on the slab. For the critical point, we have found in question A, which is 2 over 5 and negative 7 over 5. Then we just have to substitute in this equation, and we have got 73.8 degrees Celsius. For explanation, this slab has a saddle point. Indicate that the temperature is increases in one direction and decrease in another direction. And there is no local maximum or minimum in this slab, which means that the heat is unevenly contributed. So this tells the engineer that there is more than one direction of temperature change on the slab. So because of uneven heating, so it can cause expand in one direction and compress in another direction, as I said just now. So this might lead to crack or stress. So to prevent that, the engineer should carry out the cooling and insulation for this path and this slab. For the discussion part, we have used the multivariable function to represent our temperature distribution, and we have used partial differentiation to find our critical point. From the critical point, we can determine whether it is the set point, local maximum or local minimum. From this calculation, we can know that our critical point, which is 205 and negative 705, is a set point and not local maximum or local minimum for this concrete slab. So this indicate that the temperature is increased in one direction and this decreased in another direction. So from the calculation just now, we can know that the temperature is 73.8 degrees Celsius, which higher than the base temperature of 70. So this can be mean that the heat is unevenly contributed and ununiformly, and the concrete may experience higher thermal stress. Okay, so for the last part, local extreme value can not only to determine the point for temperature, but it can also determine the center point, local maximum point, or local minimum point for the stress, deflection, drainage design, foundation design, and also material optimization. Okay, thank you. That's all from me.
Hi, my name is Tan Musian, and now I'm going to talk about conclusion. This project investigated the temperature distributions across a concrete slab using the mathematical model, which is Txy equals to 70 plus 5x minus 4y minus x squared minus y squared plus 3xy. Through detailed analysis, we identify a critical point at 2 per 5 and negative 7 per 5, which was classified as a saddle point using the second derivative test. The temperature at this point was calculated to be 73.8 Celsius. These findings indicates the presence of uneven thermal gradients within the slab, which could potentially lead to internal stresses, microcracks, or long-term structural concerns due to differential expansions and contractions. The study successfully applied fundamental engineering math techniques, including partial derivatives, critical point analysis, and the Hessen's determinant to solve a real-world engineering problem. This highlights how mathematical methods can provide valuable insights into physical behavior, particularly in civil and structural engineering contexts. In conclusion, this project demonstrates the practical value of mathematical analysis in engineering. By linking theoretical concepts with real structural behavior. It provides a deeper appreciation of the role of temperature distribution in material performance. And that's all for our presentations. Thank you for listening and have a good day.